Good evening, one and all. This is Dr. P. Srinivas. Welcome to the video lecture series on signaling systems. Today, we are going to discuss about the response of linear system. Now, already we know the linear system. The definition of linear system is the system satisfies both homogeneity and superposition principle. Then we can say that system is a linear system. I am considering an LTI system. LTI means linear and time invariant system. For this linear and time invariant system, it has a impulse response. Impulse response gives the behavior of the system. Now I'm applying input signal for this LTI system, x of t. In response to the x of t, we are going to get the output is y of t. Now the formula for y of t, for obtaining y of t from the LTI system is equal to x of t convolution with h of t. Here x of t is a input signal, h of t is impulse response of the LTI system. Now we know that convolution means the common area between, to find the common area between two signals. So it is the general formula for convolution, integral minus infinity plus infinity x of t minus tau into h of tau d tau. We are changing that variable. Here x of tau, h of tau is a, we are not changing, we are not moving. But this input signal we are shifting based on the tau limits. Then we are going to find the common area between these two signals. Now, the input means we have different standard inputs here. So impulse is a one input, unit step is a one input, ramp is a one input, exponential is one input, DC signal is a one input. So we have different standard input signals. Now I'm applying for this an LTI system. I'm applying the input is a impulse. So x of t is equal to delta of t. Impulse means delta of t. So x of t is equal to delta of t. You know about delta of t. Delta of t exists at only at time t equal to 0 and it is 0 otherwise. So the input for this in LTI system is a delta of t. Then if we substitute this instead of x of t minus tau, delta of t minus tau, within this entire interval of minus infinity plus infinity of tau duration of interval, this delta function is existing only at time t equal to tau. So t is equal to tau, h of tau is going to become h of t, and delta function, delta of 0 is 1. So whenever for an LTI system, input is a delta of t, output is a impulse response. So y of t is equal to h of t. So it is about the importance of uh, impulse response. Next one is frequency response of the system. Now, so far in the Fourier transform, we have concentrated only on converting a time domain signal into frequency domains. So usually, whenever we are going to be convert a time domain signal to frequency domain signal, we are going to consider the transformation is a Fourier transform. Now, instead of signals, suppose if you want to analyze the system is a any type of system. So the system we are going to be analyzed with the Fourier transform. That is nothing but frequency response. So the system is analyzed in frequency domain. So whatever we have the relationship between input and output for an LTI system, that equation again I am considering here. Y of t is equal to x of t convolution with h of t. Now, if we apply Fourier transform on both sides, we apply Fourier transform on both sides. Y of t Fourier transform is y of omega, and we know according to convolution time domain property, convolution in time is multiplication in frequency domain. So input is x of t, that Fourier transform is x of omega. Impulse response is h of t, that Fourier transform is h of omega. So convolution time is, if you see in frequency domain, it is multiplication frequency. Now, h of omega is equal to y of omega by x of omega. If you want to find out y of t from the frequency domain, just simply apply inverse Fourier transform for this. You will get the y of t from the frequency domain. Now, h of omega is equal to y of omega by x of omega. It is nothing but transfer function of the system, nothing but frequency response. So this h of omega plays very important role in these signal systems. So you see, this y of t is equal to convolution of x of t with h of t, and then if you apply Fourier transform, convolution time is a multiplication frequency. So it can be right whether it is in a omega or it is in f. Some books are following with omega, some books are following with f. No issue, no problem. You can follow any notation. So finally, h of omega is equal to y of omega by x of omega, or h of f is equal to y of f by x of f. So it is nothing but frequency response of the system or transfer function of the system. Now, if you take one problem on this impulse response, you see this problem. The impulse response of the continuous time system is given by h of t is equal to 1 divided by RC into e power minus t by RC into u of t. Determine frequency response and plot the magnitude and phase. So h of t has given, he has asked that frequency response. So frequency response, just simply apply Fourier transform of h of t, you will get h of omega. So h of omega is equal to, you know that formula, previously Fourier transform formula, Fourier transform of h of t is equal to h of omega is equal to minus infinity plus infinity, h of t into e power minus j omega t into dt. Now, this h of t, instead of h of t, we are going to write 1 by RC, e power minus t by RC into u of t, and e power minus j omega t into dt. So, you substitute this h of t, and 1 by RC it is not a function of time. So, you write outside of integration. So, u of t, you know about u of t. U of t is equal to, it is a unit step function. It is a 1 for time t equal to time t greater than or equal to 0, and it is 0 otherwise. So, integral minus infinity to plus infinity, the limits are going to be changed from minus infinity plus infinity to 0 to infinity. E power minus t by RC into e power minus j omega t into dt. Now, you can you take minus t is a common factor, and remaining terms, if you observe, here there is a j omega plus 1 by RC. Now, it is like a e power minus t or e power minus at, like that. So integration of e power minus at is equal to integration of e power minus at divided by minus c. So you see here, integration of this one, e power minus t as it is we are going to get, and then the e power minus at by a, instead of a, we have here 1 by RC plus j omega. So divided by 1 by RC. Now you substitute these limits, anyway it is a constant, you write outside. Now wherever we have a t, instead of t, we are going to substitute these limits. So here e power minus t, instead of t, if we substitute infinity, this term going to be 0 minus of e power minus 0. Already there is a minus gets cancelled. So finally, h of omega is equal to 1 by RC into j omega plus 1 by RC into, here whatever it is equal to, 1, if you take RC, it is in the denominator, to multiply this one, 1 divided by 1 plus j omega RC. If you want to calculate magnitude and phase spectrum for this, so simply, magnitude of h of omega, root of real square plus imaginary square. Real value is 1, imaginary part is omega into RC. So magnitude of h of omega, we are going to be calculate. Here it is somewhat complicated analysis as done, but this is not necessary here. you can simply take magnitude of this one. So you will get 1 divided by root of 1 plus omega r square, this one. And coming for phase angle also. What is the phase angle of numerator? There is no any imaginary part, 0. In the what is the phase angle of denominator part, denominator term? Tan inverse of imaginary part by real part. Here omega r is imaginary, real. So whenever the phase angle is coming from denominator to numerator, it is a minus. So numerator the phase angle is 0. So finally we are going to get minus tan inverse of omega r. But here some complicated analysis has done, rationalization of this. That is not necessary. Simply, we are going to get h of omega is equal to root of 1 plus omega rc whole square, and phase angle of h of omega is equal to minus tan inverse of omega rc. So if you substitute different values of omega and assume rc is equal to 1. So if you draw the spectrum for this, the spectrum different values of omega, you tabulate different values of omega, the spectrum is like this. Today, I'm going to stop this class. We will see in the next class with another topic.